This presentation is for the Hanyang University Construction Engineering Design Assignment 2. The Marina Bay Sands is an integrated resort with a hotel, casino, retail mall, as well as convention facilities and entertainment venues including theaters, nightclubs, and a museum. The distinctive architectural features are the three 55-story hotel towers, the cantilevered sky park that connects the rooftops of the three towers, the atrium that runs through the lower floors, and the lotus-shaped Art Science Museum. For this project, we will be mainly focusing on the construction design of the Marina Bay Sands Hotel. In 2004, the Singaporean government considered the prospect of lifting the long-standing ban on casinos with a resort development plan for the Southern Islands. During that year, the government carried out a study on the economic, tourism, and social aspects of having a casino within an integrated resort. By March 25, concept proposals for the Marina Bay Integrated Resort were submitted by consortiums from all over the world, with the highest bid of 5.8 billion Singaporean dollars. The following month, the Singaporean government confirmed in Parliament that the two integrated resorts with casinos would be built, one including the Marina Bay Sands. In May 2006, the Las Vegas Sands Corporation was awarded the rights for the Marina Bay site. The company's distinctive design elements of the proposed architecture were cited as key factors in its winning bid. Construction began soon after the project was awarded. However, Las Vegas Sands was reported to be in financial trouble in 2008 due to the influence of the global financial crisis. Las Vegas Sands had trouble to secure the financing for its project, getting close to bankruptcy a number of times. The project continued to suffer construction delays, which were attributed to the high prices of concrete after an embargo on sand exports by other countries and the bankruptcy of subcontractors. Heavy rainfall and labor shortages also contributed to the delays and the project's escalating costs, which amounted at the end of 7.7 billion Singaporean dollars. However, the Las Vegas Sands announced that the Marina Bay Sands would start operations in April 2010 and officially opened on the 23rd of June that same year. And now, the Marina Bay Sands is one of the most profitable properties in the Las Vegas Sands Group. The architect for the Marina Bay Sands is Moshe Safdie. His works are known for their dramatic curves, arrays of geometric patterns, use of windows, and key placements of open and green spaces. For the construction, Las Vegas Sands awarded SsangYong Engineering and Construction for the guarantee to complete the project within 27 months. For the construction, SsangYong AC was awarded numerous awards and also achieved 12 million man-hours for zero accidents. The design of the integrated resort became iconic for Singapore and even changed the image of the country. The curves of the building and the sky park are unique architectural features. However, the design faced some major issues, which we will be discussing in the next chapter. To define a project as impactful as the Marina Bay Sands, let's first take a look at the design concept. The shape of the hotel tower was inspired by poker cards leaning against each other. The poker cards are a good design concept for the resort and fit within the casino theme. Representing two cards leaning against each other, each hotel tower consists of two buildings and begins to meet each other at about 20 stories high. Another design concept is Singapore's Gateway. Each of the hotel towers has a huge structure, with the sky park on top of it. The sky park connects the three different buildings as if they were one. The design concept for the Marina Bay Sands follows the three E parameters: explore, exchange, and entertain. The tapering of the building was then conceived due to the continuous atrium along all three towers. Tapering the building has the following advantage. The effect of wind and earthquake forces create a sway in the building. In other words, the top of the building should not deviate beyond a certain dimension from its position. This effect is minimized if the base is wider than the top. For the standard use and safety requirements, the design has issue points for the axial forces, shear forces, deflection of the structure, and the bending moment, as the design distributes these forces in an unconventional way in comparison to normal buildings. The movements of the towers were observed and studied for safety, such as angular rotations at the top, maximum deflection on elevations in vertical and lateral directions, differential settlement between straight and sloping walls, differential movement between the towers, which could affect the deflection stage of tower behavior of the sky park. The design issues caused by the conceptual elements that were mentioned can be summarized as follows. 1. The steep inclination. 2. The height of the superstructure. And 3. The cantilever deck. 1. The steep inclination. According to the simulation results, the east building collapsed before reaching the height of the 8th floor because of the overturning forces caused by gravity, similar to how dominoes fall down. Each of the three 55-story hotel towers has its unique geometry with varying curvatures. The dramatic curve of Tower 1 reaches up to 52 degrees, which is an astonishing 10 times larger than the slope of the Leaning Tower of Pisa. 2. The height of the Sky Park. The Sky Park merges the three hotels into one superstructure. This structure could be built after all the three towers were completed. The idea of placing a huge structure safely at a height of 200 meters above the sky shocked people, but is from a structural viewpoint very feasible. The Sky Park seems like it is one construction, but actually consists of extensions on the hotel floors, bridges, and one cantilever sky construction. Which brings us to 3. The cantilever construction. A cantilever is a rigid structural element which makes it possible to construct overhanging structures without external bracing. The huge ship-shaped structure includes an infinity pool, gardens, a club, and decks. In addition, the deck was the longest habitable cantilever observation deck without any support. The Marina Bay Sands is located on reclaimed land, which is a land made by making embankments on the seashore and by taking the water out of it and filling it with sand. The Marina Bay area has had several phases of reclamation. The latest was completed during the mid-1990s. Most of the Marina Bay Sands development sits on the latest reclamation zone, which leads to many problems for the project to be realized. Let's take a look at the site geology here. The cross-section along the CC line is shown on the right. It is sand infill overlying deep soft clay marine deposits above an underlying very stiff to hard old alluvium layer. The blue layer consists of soft marine clay called kalang. It was too soft to support the huge weight, which caused significant challenges to the phase of excavation works. The bottom layer is an old alluvium layer, which is the hard layer deposited for a long time under the soft marine clay layer. Built on these lands, Marina Bay Sands experienced the following problems during the excavation. 1. Weak soil. The ground is weak because it's newly created. 2. High soil pressure. Due to the high water table, high soil pressure is continuously applied during the foundation phase. Then, how to overcome both problems in the foundation phase. To overcome the weak soil problem, a lot of barrettes and board piles are inserted into the hard, stiff alluvium layer, the yellow one. Unlike the conditions in Korea, where a 10-meter excavation would reveal the base rock, this site required 30 to 40 meters of excavation. At this time, load capacity confirmation had to be addressed. So-called O-cell technology was used. It was the bidirectional testing method. Load test programs using Osterberg cell bidirectional testing method was intended to confirm foundation load capacities. The O-cell bidirectional technology was chosen for the following reasons. To confirm that the test design loading requirements were being met. For its ability to isolate and load foundation bearing strata, which was key to schedule that required loading capacity confirmation prior to site excavation. For its ability to separate the end bearing and skin friction components of foundation capacity, and for its ability to provide high test loads even with the deep foundation cutoff levels. This table compares the advantages of the bidirectional load test with the conventional method. We know it's a way to save money, time, and even check stability. Gauges are connected up and down the O-cell plate, and several sensors, including strain gauge, are attached at regular intervals. You can check the stability of a POW by placing it where it's placed and monitoring the actual behavior of the POW. In the excavation phase, a lot of temporary struts are used, making it difficult for both excavation and construction of the structure. To overcome this problem, the circular diaphragm wall method was applied. Conventional rectangular shaped walls had to be supported with steel struts to prevent the wall from collapse. However, the circular diaphragm walls, called D-walls, do not require any internal supporting struts, so this method can remove the temporary structures and reduce the construction period. This experiment shows that the round-shaped cofferdam is stronger in pressure than the square cofferdam. This is because for circular shapes, the force is evenly distributed along the wall. The 120-meter diameter cofferdams were among the largest ever deployed in Singapore, and notable for excavation depth, down to 80 meters below ground. They allowed work to progress across the site simultaneously, with either the excavations to the north or south being able to be in advance of each other. Three-dimensional analysis were carried out to demonstrate this flexibility. In summary, Marina Bay sands can overcome their first problem, mainly caused by reclaimed land, such as weak soil, high soil pressures, and a short construction period, by using deep foundation piles and the circular diaphragm method ingeniously. The main structural members of the atrium are the rectangle hollower sections, and the base is pin connected. The next phase of hotel towers are construction engineering issues, which we will handle these contents next week. Marina Bay Sands is connected to a district cooling system to use energy more efficiently. Hotels' air cooling condition makes use of water-cooled chillers, which are nearly 80% more effective than air-cooled models. The heat obtained in this process is used as hot water supply in hotels or restaurants. And using 60,000 energy control points, that system automatically dim or brighten light in public spaces depending on the time of the day and the weather conditions. By using this system, Marina Bay Sands saves over 55 million kilowatt hours per year. There is a sky park at the top of the hotel. Sky Park has 12,400 square meters green oasis of 250 trees and 650 plants, some up to 8 meters tall. The Sky Park is home to over 900 plants and trees. The Art Science Museum's roof also has an environmental friendly aspect. Rainwater is collected in the roof of the Art Science Museum by rain harvesting system. The water collected is recycled in the building's flush water toilet system or irrigation water. It saves enough water to supply more than 800 households in Singapore every year. This was our presentation about the Marina Bay Sands Hotel for the second assignment. Thank you for watching.